the rig flexibility that we cannot model in a numerical model. So the main thing we need to highlight here is that you can see there's around the peak capacity is around 2% variation. So this is a very good agreement with the experimental results. So by looking at the experimental and numerical curves, we can extract some data. So it is not just the peak displacement agreement, but across the tip displacements throughout, you can see how the numerical and the experimental curves are behaving and how it is in a close range of accuracy within the experimental results. Also, the stiffness degradation with the experimental and model also coincides very accurately. So another main thing that I need to highlight here is the failure mechanisms. So even though we did not ask the model to predict the failure mechanism and where the failure would occur, we got a good accurate prediction in the pile itself. So you can see in the experimental results, we got tensile crack in one phase, and the other side, the opposite phase, it was compression cracks, compression crushing the concrete. So in the numerical analysis, you can see tensile bands developing in the pile, replicating the exact scenario at the designated locations. So here's the compression localized area as well. So this is another good example to validate our numerical model. So this is the complete setup under the loading. So with the pier head, you can see there are no connection loss or any cracks in the grouts, and only the pile is failed. So our main objective was to make sure that our connection is robust. Then afterwards, we can optimize whatever the beam section and any grout sections to accommodate the design perspectives. So just to give you an idea, so the moment that was transmitted through the joint was around 76.8 in the experiment. By the model, it was around 75.4 kilonewton meters. And by looking at the response, the design of this pile that the manufacturers are using, we found it around 40.6 kilonewton meters. And the spun pile was again modeled in response 2000 to give further validation. It was around 48 kilonewton meters. So it is 1.6 times the strength that we expected. And also, even for that load, the grouting or the connection is in contact. So we can optimize the design further in order to make sure the pile is not going to fail, but we can make whatever the critical elements fail before that. So by looking at this, we can draw some conclusions. The first conclusion is, according to our aim, we have been able to prove our capacity. So the double collar interlock transmitted to a moment at 76.8 is 1.6 times the ultimate fractional capacity of the spun pile specified. And again, one more important thing is that the ductile directed failure. So it was not just a brittle failure, so it has a long plateau before failing. So that means the pile is at ductile failure, which gives ample amount of time to work on that, and we can even retrofit whatever the failure mechanism we have. And another main thing is that the model is very capable of predicting what happens and where the failure would occur. So even before building any experimental setup, we can validate through our numerical model. And since the joint is not the critical part, we can optimize whatever the elements we need. And this is another conclusion is that we can opt for a durable marine construction by using these precast construction methods. So here are some references, and thank you.
Thank you for the presentation. So it's time to move to the next presentation. We have two more presentations. The paper ID 380, development of ultra high performance fiber reinforced concrete, retrofitting framework for reinforced concrete beams. The presentation is by RSSA Vijay Sundar, I Abekon, NMSH Bandara, and KK Vijay Sundar. The presenter is Mr. Abekon.
Good morning all. I'm Mr. Abekon and my presentation is on development of a UHPFRC retrofitting framework for reinforced concrete deep beams. So this is my overall outline of today's presentation. I'll initially give a brief introduction followed by the aim and objectives. Then I'll talk about my methodology and finally results and conclusions. So starting with the introduction, I'll initially give a brief context on reinforced concrete deep beams. So deep beams are beams with generally low span to depth ratios as shown in these images. So due to that, these reinforced concrete deep beams tend to fail in brittle shear, which is sudden and with almost little to no warnings, which is highly unfavorable to us, which is why we chose these deep beams for strengthening purposes. And for this strengthening work, we selected the material ultra high performance fiber reinforced concrete, or in short known as UHPFRC. So UHPFRC is a relatively new cementitious composite with enhanced mechanical and material properties. Its constituents generally includes cement, microsilica, fine sand, superplasticizer, water and steel fibers. Unlike in conventional concrete, UHPFRC generally does not include any coarse aggregates, which results in it having a denser matrix. And due to this enhanced mechanical and material properties, UHPFRC is used in several applications, which includes tunnel lining or bridge deck overlays, or in specifically, like our case, structural retrofitting. So these are the aim and objectives of our study. The aim is to develop and experimentally validate a UHPFRC retrofitting framework to select the optimum jacket thickness required for a two-sided jacketing configuration that can shift the failure mode of these reinforced concrete D-beams from brittle shear to ductile flexure. It has three main objectives, starting from the development of the UHPFRC material, and then the prediction of this retrofitting jacket thickness, and finally the experimental validation. So for this, we followed this methodology, starting from the UHPFRC mix development with locally available materials. Then the retrofitting framework. So the first part is the assessment of control and retrofitted beams. With that, we selected the optimum jacket thickness which was required to shift the failure mode of these beams from brittle shear to ductile flexure. And then finally the experimental validation, which included full-scale beam testing, and finally the comparison of results. So the UHPFRC material that we developed is this. The mix design is shown in the right side table, and this material had a compressive strength of 119.5 megapascal, which is a significantly high value, and a tensile strength of 9.1 megapascal, and a flow value of 157 millimeters, which shows its good workability. Then the retrofitting framework, we started with the assessment of the control beam. So we conducted sectional analysis and a code-based approach to calculate the flexural and shear capacities of this control beam. So as shown here, the shear capacity is the lower value, so in which case it's the critical and governing value for this control beam. So therefore, this shear capacity being its governing factor, it's our shear strengthening approach can be justified. With that, we moved on to the assessment of the retrofitted beams. So this plot here shows the variation of flexion and shear capacities of this retrofitted beam with different jacket thicknesses. So as it can be seen here, both the flexural and shear capacities have increased with the increase of jacket thickness. And specifically at around 30 to 40 millimeter region of this jacket thickness, the failure mode or the critical load has shifted from shear to flexure, which is why we selected the 40 millimeter jacket thickness as the optimum thickness which is required to shift this failure mode from brittle shear to ductile flexure. So with that, with this two-sided jacketing configuration of 40 millimeter jackets selected as the optimum thickness, we moved on to the experimental validation part. So for the experimental program, we conducted full-scale beam testing with 3-point bending tests. as shown here. So the important part is the results comparison between these predictions and our experimental program. So here I have shown the comparison of load capacities. As shown here, the black color line shows the response of the control beam, and the red color line shows the response of the retrofitted beam. So with this experiment, we identified an increase of 103% of the load carrying capacity due to this retrofitting configuration. And the key point that has to be noted here is the validation of our retrofitting framework. So as shown here, between the prediction of the load carrying capacity that we got from the retrofitting framework and the experimental results, there was only a 0.3% error, which indicates its high predictive accuracy. And the other thing is, as expected from our retrofitting framework, we were able to verify that this 40 millimeter jacket thickness managed to shift the failure mode from brittle shear to ductile flexure. So these are the comparison of failure modes between this control beam and retrofitted beam. So as shown in the left side image, it's the crack patterns of the control beam. It can be seen that there are dominant diagonal shear cracks in the control beam, and it fell in brittle shear at around 185 kilonewtons. As for the retrofitted beam, we can see there are ductile flexure cracks in the beam, and due to this retrofitting configuration, the initial cracking was also delayed to around 215 kilonewtons, and it fell in flexure mode at 376 kilonewton load. And finally, this is the overall summary of everything I've discussed so far. So initially we developed a UHF-RC material with locally available materials, and then we moved on to the strengthening work of this control reinforced concrete deep beam, and we managed to increase the load carrying capacity by 103% while shifting the failure mode from brittle shear to ductile flexure. And the key point again is the validation of the retrofitting framework, which showed only 0.3% error. And finally, the conclusions. Initially, we developed a workable UHPF-RC mix, and then with approximately 120 megapascal compressive strength and 9 megapascal tensile strength. And then the other important part is the predictive framework that we developed. And then we selected a 40 millimeter jacket thickness using that framework as the optimum jacket thickness for this selected control beam. And with the experimental validation, we only got a 0.3% deviation, which validates our framework. And then the capacity and failure modes of these beams, the two-sided jacketing configuration that we used increased the load carrying capacity of this beam by 103% and managed to shift the failure mode from brittle shear to ductile flexure. And then finally, the other important point is the composite